Okay, back in business. Welcome back. In the previous video, we have demonstrated the terminology and overview for the Electrostatic-Sandbox SDK, and it wasn't a very good video, by the way. But anyway, we will now continue and examine the source code and the files on GitHub that are technically on GitHub, but we will examine them offline on Android Studio. You can use Android Studio or IntelliJ IDEA for this, or any other IDE of your selection. It's all, like, as you could see, we use scripting, right? So this is a scripting architecture. This is the build architecture I am utilizing, the Electrostatic-Sandbox framework building architecture. You could read this, but it's based on the finite state automata. So it's based on automata pattern. That's the mathematical model. Basically, it's a computational, or that's a computational model that entails a transitional states with inputs, right? So this is the first order logic that we basically have. This is a software specification for the first order logic that we have, and this is the, and how to using this one. This is the build architecture here. So we have the build instructions, and the build instructions is the input to the native build and Java build. So we have two components. This is the front end API. So basically the build architecture entails using a front end API, and it's subdivided into a native build scripts and Java build scripts, right? So and we pass the build instructions. So what are the build instructions? For example, I want to build this electrostatic sandbox for the AVR. This is totally different, a totally different build instruction than when building for Windows, for example. That's technically different. So this is the build instructions. You pass it to the native build and the Java build, and then you actually get another build instructions, right? This is done by the front-end API. It passes the build instructions to the base building APIs, or the base building frameworks that I'm using, which is Gradle for Java, CMake for C++, right? C++, all right? Or it actually, if you pass a faulty instructions, then it goes to the exceptional automata. So if you pass good build instructions and supported build instructions, it will continue the finite automata till the terminal state, which give you a deployment at the end, right? But if you pass faulty instructions, then it will terminate with an exceptional automata. That faulty could be bad tokens, unsupported systems. You try, for example, to build for Android that's not currently yet supported, then it will end up crashing the build with an exceptional automata. That's the exceptional automata. Let's say that this is not supported, or it will give you an unidentifiable error, all right? And you can have write errors. For example, you're trying to build on a read-only file system, so then give how I might get you an output if you build for a read-only, if you build on a read-only file system, and out of memory errors, right? The normal automata continues from the platform build script to the system dependent build script. So the CMake generates a make file, or a Visual Studio script, or a PowerShell script, depending on how you and what what system dependent build you will generate, right? But most of cases I don't know much about Windows, but on Linux we use the makefile. There is also a build system known as Ninja that could be generated through the CMake, but I use the makefile, the appropriate makefile, right? The Gradle OpenJDK, it delegates directly to the Java tools, right? Particularly the Java compiler, the Java C. Then we have the compiler linker input that gets to link the libraries together, and it resolves it leads to source code operations. For example, native code resolve, Java code resolve, libraries operations, executable operations. It ends with assembling the input. So this basically, you build the compilation units and then you link them together, right? And then you package them into static libraries, for example, or either static libraries or dynamic libraries, right? We have both options in this case. And the final is the assembling the output, which gives you a deployment. You can read all this, but I'd like to go over the source files or the source code that we have. So the project is initially a native project with a Java binding module. That's the Electrostatic-4j. You have the native modules. Actually, there is a minor change in this, and this might be a little faulty, because now the project is now a Gradle project. So you can find the Gradle project at the root, the Gradle files at the root, and then this is the Electrostatic-Sandbox framework. This is the project. This is our project, all right? Those are for the website, so you could glance over them. This is the IEEE 1516 guide. You can find the C++ API copied directly from IEEE 1516 with their license, and the one for Java. And this is just the roadmap for the Electrostatic-Sandbox. These are a couple of miscellaneous files and not yet well cleaned, but this is the main project, right? So the Electrostatic-4j is a Java binding module. And it has the migrated libraries, right? So we currently have only the actual Electrostatic-4j, the actual serial 4j. This is the only one that we have for now, and the others are not yet copied or are not yet migrated. This is the only one that's migrated, and it's running perfectly fine, right? However, we will manage, and we will see how to manage the release cycles, because release cycles will be different from the serial 4j project and the rest of the API or the rest of the framework, right? So these are the actual Java binding API or Java binding modules. This is Electrostatic core. This is our native module. This contains the C. This all in C only, no C++ and no Java. All right. This only in C99 and the GNU extensions. All right. You can find the source, the includes, and the libraries. That's the part that I talked about in the previous video. That we have the electrostatic and the electrostatic primer, or the primer, right? The primer or the primer is a minimal viable product that we will use to fire our project, and it will include the early released libraries, while the long-term support, the LTS, will be included in the electrostatic, and that's the production. So this is the production route, and this, or the production package, and this will be the early released package, right? We are now working on the early release package. You can find some APIs, some good APIs for algorithms, for example Arithmus, Algebra, you can find the switching and, for example, a way to get the inputs and an output. Get a multiple inputs. For example, this is an array of pointers or a pointer to pointers, and you can get a contiguous, like a contiguous buffer of pointers together and try to AND them and get them to the output. For example, we will have separate videos for the project is included, but now I want you to get grasp of this structure, right? So this most of these are the actual software infrastructure, software and networking infrastructure. The COM for communication, the platform for the specific platform, and the utilities. You can find a loader, a del loader API here, and unit testing API. Those are literally finished, right? And you can see that the code completion and the navigation is working fine on the IntelliJ IDEA or Android Studio or whatever, right? Those are the scripts that you want to run. So those are linked to the scripting, right? You can find the scripts here in the helper scripts, CI/CD. Those are, this is the front end API. This is the front end API I'm talking about. This routes to either the CMake lists here or the actual Gradle, the actual build Gradle, for the Java, part. So this routes to either the CMake. We are using a single CMake file, and we build instructions from the bash script or the front-end API to the CMake or to this Java, to this Gradle, right? So either to the CMake or to the Java, like that, the one displayed here, this back to here. So the front-end API, this is the bash script. You have a native build. That native build is going here. The native build API is going here. Compile electrostatic. That's the primer. We compile all and compile for Android, and you can find this here. Compile all. That's compile all. That compile electrostatic. It compiles for Linux x86 64 and x86 only. And this compile all delegates the code or delegates the runtime, the compiler runtime, to this one. This is the final compilation, right? It calls the abstract compiler. It calls the abstract compile here, right? Which delegates to the CMake script there. So this delegates to the CMake script that we have, right? It CDs on the CMake directory and delegates to the CMake that we have, and it passes the instruction, the build instructions, to the CMake script there, and that compiles and links and assembles the the actual final library into two types: a static library and the dynamic library. We have two deployments, right? And then it CD back, it changes directory back to the main, your start directory. This is the front-end API that we use. It's an abstract API. It could be used with any type of systems, right? To build for any type of system. That's this is a front-end API for the native build, okay? And this is for the Java build, the Electrostatic 4J. It uses the same abstract. It uses the same abstract or another one. It uses the same abstract compilation, and it compiles. It adds the GenI headers, the Java Native Interface headers for the system, and we only support now GNU Linux. And the GenI headers, the actual GenI headers, the include directory, right? This is one. This one is for examples, and the example is different. It uses a different script. Yes, the example uses another CMake list because it outputs an executable rather than a library. So I differentiated between both an executable and a library, right? By the way, Serial4J also has a Serial4J native that is migrated directly, and you might find duplications in code, but it's written in C++. The only library written in C++, because we have migrated it, so I'm not going to rewrite it. We already did this, but the actual library, the actual native Serial4J native is built using the same script there, right? So this how it works. This one here is a configuration, an Android Studio configuration. I wrote here, down here you can find here in the Studio Run configurations, and it will be configured automatically when you open the Android Studio. Also, we have Fleet, a configuration for Fleet also works. But for example, I want first of all, before running anything, you have to run the setup. There is a script that's known as a setup environment, right? You can use the GitHub workflow to guide you on the steps to start building the SDK. So you will fork and clone, and then you could either follow this build test one, is follow this by running the setup Electrostatic-Sandbox first and wait until it setups. And what it does, basically, it installs and downloads and installs and configures the toolkit chains that will be used, the Gradle, the CMake, with a specific CMake versions that I'm using, 3.19, okay, and it adds some what is called like shortcuts for the for those binaries, right? We can open this to get insights as well during this. I know this might be a long video, but this is the only way to do this, right? So it basically prepares the sandbox workspace, and you can find this sandbox workspace here. If we were to cd on the /opt/electrostatic, it creates this folder and it adds these, downloads these kind of stuff, and adds soft links to them as well. So setup JDK, setup Gradle, we use JDK 20 by the way, CMake, AVR Dude as well, and NDK, and those are commented for now. And then it creates symbols and add user to serial groups, which is very important to be able to run, to be able to enable your user, your current user or your default user to run, to initialize, to open and write and read on serial drivers, right? Now we could you need to run this before you start. So if you open this, you could say, let's you say that there is a setup sandbox. You run this setup sandbox and it starts to set up. I'm not going to run it because I have the files already there, and you could run this, and this is the first thing you need to run before you do anything. Then you need to build the Electrostatic SDK, the native code, this native code here. Where is it? This native code, the electrostatic core. You build it, which builds into Linux, x86 and x86-64, two libraries, shared object file and an archive, right? But the Android is not working for now, right? You can, if you have a fix for this, you can tell me that you can submit a PR, and I welcome this. All right, so I will run this build electrostatic sandbox, and you can see that it will run. We have no errors here. All right, it builds the project, and it builds first as a shared object file, then in the archive, and then this for the x86. The former was for x86 64, and now it starts building for Android, which will fail because there are some linking issues. There are some libraries that are that's not found there. And finally it finishes. Then we will try to run an example as well. For example, we want to run, and those examples, by the way, also examples are considered from the front-end API. And the beneficence of, by the way, the beneficence of the front-end API of the building is that it's now agnostic. It's generic. You could use this even or not bad. For example, you could use Vim or even any text editor. You could use any text, or Emacs, even Emacs. You could use Emac for this, right? You don't need to use Android Studio, but I use it for code highlighting and completion navigation system. And also it provides documentation for Java and C++. So it's a very cool IDE, but you could use anything because we base the actual build on the actual build on a front-end API that links directly to the platform independent building tools like CMake and Gradle, which then generates a platform dependent code, or links directly to a platform dependent codes. Just for example, the Gradle, it links directly to the JDK, which links directly to the GRE. The GRE is a platform dependent, right? This is the case. You could, for example, see this. They compile examples. It also compiles, and this only compiles. I think this only compiles examples and doesn't run it. I can't remember exactly. This compile examples. Let's see the test electrostatic. Yes, it only compile. This compiles an example which calls this front end area. So these are shorthand for the CI/CD. You want to use these directly. The script that is present here uses them directly. So for example, we will take an example. I want just to get you started because it's really clogged here, and it's really entangled and hard. This one here, for example, this is a unit test. So it runs. This is the script bus that it runs, and this is the options. They are compile time options. So in this case, I pass the low unit test, and it starts compiling and linking against the Electrostatic-Sandbox library, and then it runs the example that we have. All right. So let's try this. The test, unit test, unit test, hello unit test. We run this, and then as you could see, test predicate is not existential. That's a unit test. That's an output for unit test. But we have successfully built and we have successfully ran the actual test example. All right. Now I want to show you a last thing. I know the video is taking too long. This one here is an Arduino that is running Shift AVR with the example of an example of ADC, right? And UART. So it basically reads from this, right? The ADC reads from this, and then it transfers the data. It encodes the data to the UART, and then the UART passes the data in the serial USB in the CH340, which converts the UART to USB serial, right? And we will use the USB serial now with the this is technically a USB serial converter, right? The CH340. We will use it directly with the USB serial of my laptop and see how Serial4j deals with this one, right? Let's start this. So we have the example here, a JMonkey engine example, which is, for example, this one here, the run JMonkey engine car simulation. And we want to run this example. Let's first test the example without anything, and you should find a failure for file not found exception. And that work is yes, a file not found exception. No such file exception, no such file or directory. Device port is that we try to open a port which is not actually there. So let's now get this into running. This is going to run. We will flip the camera for now. Yes, we flip the camera. Now let's do this. This one here. Alright. And then back to this, and back to our example. Now running this example, now we have the serial device connected. This is basically a byte flow or data flow architecture. So this opens a pipes between both, conceptually opens a pipe between both based on the file systems. Alright. And now we have the game and this beautiful hardware device that is connected over the serial. This is a small or minute model for distributed simulation. Alright, as you could see, we could simulate the movement of a car without actually bringing a real car. Alright, this could be, for example, this could be a rocket, another car. We could actually simulate the rocket launch, rocket abort, and even rocket crashes, right? And rocket separation phases. That's a very cool and scientific way of using computation. This, and it's one of the visions now is that we want to simulate these kind of stuff because the circumstances is really different. So for example, you don't have a car that jumps and crashes into something, or that's inside the playground and moves a metallic ball, for example, or you could actually even simulate military operations into this. So it really depends on your project. It's not something that but this is very different from the SDK. This is a different code than the SDK, right? This is not the SDK. And also we have another thing that is taken from the Electrostatic SDK and not Serial4j. It's not presented Serial4j. This file, the file validation API, which checks for paroxysmal or sudden removal of the connection between both. So if I remove this connection, it will crash. Oh, didn't crash, or it crashed but it haven't. This might be, yes, it crashed. it crashed with an invalid port exception. That's an invalid port or abrupt device disconnection. Device port, because we have actually paroxysmally removed this. So I know the video is quite too long maybe, but this is the only way to show you some of the gems of the SDK. There are a lot of things, and I want to really make it happen, make the project better. And the project is open source. You can find the link in the description. Please, if you find this project useful, please consider giving me a star, fork, and if you want to contribute, just you can message me directly on LinkedIn or my Facebook. I dropped the Facebook for the Electrostat Lab. I reply also there. All right. So I hope you find this useful. If you have any insights into this project, this is an open source project with PSD3 cloud license, right? Taken directly from the AVR sandbox, but is now for the Electrostatic-Sandbox. And I hope it really catches your eyes. And this is the end. Until next time.